Good afternoon. My name is Asad Mirza, and I am going to be presenting uh, the workshop today for 3D printing. I'm a PhD student in the Biomedical Engineering Department, working on Dr. on Rasami. So, at any point during this discussion, you can go ahead and ask a question if you want. But without further ado, let's just get started then. So, what is 3D printing? So the analogy is easiest to start off with if we talk about 2D printing. So you can imagine if you have a single layer printing, it's done usually with ink on paper. 3D printing is almost the exact same thing, but now in third dimensions. So instead of printing on a single flat sheet, you're printing layers essentially. And instead of printing with ink, you're printing with various materials. They can be plastic, elastomers, sometimes even metals. And that is essentially, at the bare bones, the difference between both of them. So I always consider it prudent to talk about the history of these technologies. It's always good to know where they come from. So the very concept of 3D printing started back in 1974 by this man named David Jones. He was writing in this column, uh, Ariadne, I believe it's called, in the journal New Scientist. And he basically theorized this idea where if you have a bunch of liquid monomers that can be polymerized into a solid by ultraviolet light or even visible light, you can stack them together and create a three-dimensional structure. And what he was essentially describing back in 1974 was SLA printing, which is one of the types of printing that we're going to be going over. So, as a sort of rough timeline of 3D printing throughout the ages, 1974 was when this happened. And then Chuck Hill embedded SLA type of printing in 1984, commercially at least. And then you have this company called Stratasys commercializing 3D printing and creating what they call fused definition modeling, which is the most popular type of 3D printing in 1990. Then we had some bioprinting of organs such as bladders that can grow cells in 1999, a functional animal kidney in 2002. And then this open source company called RepRap was founded in 2005 that created this open source printer that can replicate itself essentially. And if you look online for 3D printing designs or most popular 3D printers, you'll find that they look fairly similar. And that's because RepRap was the one who sort of founded the basic designs that they're all using essentially. So that sort of explains why a lot of 3D printers look the same, but they just have different bells and whistles. Then you had some 3D printing of human blood vessels in 2010. Then there was a woman in Norway in 2014 who was the first recipient of a 3D printed skull transplant. And then more recently in 2014, a Chinese company and was able to do 3D printing of full-on houses, so large-scale 3D printing as well. So that sort of takes you through a little timeline of the events. Now let's talk about the types of 3D printing. So there are many kinds of 3D printing you can do, but the three main types I'll be focusing on are based off their market share essentially. So we have the most popular, which is called fused deposition modeling, which is probably what you're imagining it is when you think of 3D printing. Then you have SLA, also called DLP. So that stands for stereolithography or digital light processing. And then the third one, which is less used, is SLS, which is called selective laser sintering. So let's go ahead and take a look at these in reverse order. So first, SLS. SLS printing is additive manufacturing. So essentially, the way it works is you have this bed of powder that you're going to be doing your printing on, and basically a laser goes over the entire structure and then fuses together small little polymer powders, layer by layer, creating your 3D structure. So, pros of this. It's isotropic in its mechanical properties. So because it's being supported in all sides, and all it's doing is solidifying fusing a bunch of little beads together, layer by layer. They're all sort of the same no matter which direction you're looking at. And because it's inherently built inside of this dust sort of structure, there aren't any supports needed because the entire thing is a support. And this is very beneficial for batch production. So you can imagine a gigantic field just full of this small polymer dust, and then the laser going through and making multiple pieces of some small part very quickly. Cons, because of how everything I described, it's mainly industrial for now. And as you can see here in the image, you can also get this sort of grainy surface that comes from not having a smooth finish in the fusing process. So it's not smooth and it's not watertight either. And another con is you're not like exactly able to get nice flat surfaces for these exact reasons, and very small holes aren't possible because naturally you're trying to fuse together small little beads of powder, so small features aren't exactly achievable. The second one is more popular. It's called SLA printing. Now, SLA printing is also additive, but instead of fusing together a bunch of powders, it works by having this sort of bed of photoactive resin. And what happens is the layer goes over each layer, and then selectively cures it, usually using, for example, UV radiation, and then it just sort of builds from the bottom up. So the pros of this is you can get high dimensional accuracy because wherever the laser hits is where it's going to cure and not anywhere else. And because it's liquid to start off with, you can get a very nice smooth finish, and it usually can be clear, flexible. It's very versatile in that approach. Slight con, because it's inherently has a liquid base to start off with, as in the resin, it can be brittle at times. And the resin, because it cures from UV radiation, uh, it tends to degrade with time and sunlight if you overcure it. And another downside is that see these little rods right here, these are support structures. And these support structures are required to do the printing, so you have to remove them, and that adds to post-processing time. And one thing I forgot to mention here is that resin is usually toxic, so you have to make sure you're wearing gloves and a mask and everything, and when you're cleaning up your pieces. But after it's been cured, it's usually safe to handle. And the last one is the most popular one and the one I have most experience using is called FDM printing. So in this case, you're essentially just printing layer by layer after you've melted some material. And that's essentially what this little infographic at top shows, just going layer by layer, printing it. And if needed, you build up these little supports because you obviously can't print on thin air. So you have these little support structures here, and then you just remove them and you have your 3D print. So the pros of this, it's very cost effective. In fact, I think nowadays you can find a printer for sub $100 if you look far enough. You have a wide range of thermoplastic materials available. Slight con is that it has the lowest dimensional accuracy out of all 3D printing types, but that's sort of relative based on your application. So because obviously engineering and everything, I often have to deal with sub-millimeter type of tolerances. So by low dimensional accuracy, I can get away with a margin of maybe like plus or minus 0.5 millimeters. So you sort of have to play around with that a little. And also, if you notice, because it does it layer by layer, you have these sort of visible layer lines occurring because it's doing it layer by layer. So if you don't like that visually, you're gonna have to do some post processing to remove it. And because it prints from one direction up, it's inherently anisotropic. So as opposed to the first printing method we talked about with the powder bed fusion, which was isotropic, this is anisotropic because of the method that you're doing your printing. And the last one I want to talk about is bioprinting, probably the most interesting out of all of them. So for bioprinting, it's very similar to fused deposition modeling, but instead of printing out with a filament, you print a combinational print of a scaffold material and then cells. So this is useful for fast prototyping for in vitro testing. Slight, well, probably a major con at least for this is that you have a large initial development cost, with I think even the cheapest bioprinters costing at a minimum $5,000. And if you've ever dealt with cells before, you'll understand when I say that if you so much as look at them wrong, they'll uh, start dying on you or not proliferating or contaminated. So it's very difficult to maintain the cell environment in your bioprints. And there's naturally ethical liability, as is with anything bio-related that you could potentially use in the body. So you can imagine here you have these sort of spheroid ink tablets that have these cells and scaffold material in it. you usually have this hydrogel matrix that it's printed on. So you build this layer by layer by layer, and all the little spheroids just get fused together. Then you can, if you so choose to, dissolve the surrounding matrix and the hydrogel, and you get living tissue as an end result. And here's an example of a human ear, just for demonstration purposes. But in application-wise, you can take a look at this example from Rice University, where collaborators under Jordan Miller created this alveoli model for the lung, and it mimics the body's natural passageway for blood, air, lymph, and other vital fluids. So you can see here, deoxygenated blood flows in from top. You have oxygen flowing in from an alveolar air duct over here, and then you have gas exchange occurring here, and then you have oxygenated blood leaving through this tube here. And then they also did some screening afterwards to show that they actually did oxygenate the blood afterwards. So this is just one application of bioprinting that I wanted to go over. So before I continue, any questions that anybody has?
Yes, we have one question in the chat. The question is, does bioprinting process harm actually the cells?
So it certainly can, because when you're doing the printing, if you're not careful on your printing speed or the orientation of your printing, you can cause unnecessary shear to your cells. So if you're printing in a non-temperate environment or you're printing too quickly, you can cause a small disturbance to your cells, and any kind of deviation from normal cell environment could harm them, which is why usually you have to be trained on these machines by whoever made them. Hence why they're very expensive to start off with, because usually the printer that you purchase may be $5 grand, but it comes with support and availability from the company that they'll help you how to best make your 3D bioprinting materials and such. So yeah. Any other questions? So if there is anything else, I'll continue. Right. So from here on, I'm mainly going to be talking about the most popular type printing, so FDM printing. So in those cases, you use filaments, and the most popular type of filaments that you're going to be using are listed here. So you have ABS, PLA, nylon, PETG, TPU, and PE. And here's some pros or strengths you might want to consider. So chances are, if you look around your room and you find anything that is made of plastic, I'm almost guaranteed that it's going to be made from ABS, because it's a high strength material that has good temperature resistance. And the only con really that I can think of when you're trying to do printing with ABS is that it has a very high melting temperature compared to other materials. So it's often prone to warping. And by warping, I mean if you are printing one layer, for example, and by the time you get to one section of the layer right here, this layer that you started off with right here has already cooled. And because it cooled a bit too quickly, it sort of detached from the surface that you were printing on. And then when the next layer prints, this print might have adhered properly, but this one got detached over here. And then now you have warping occurring throughout your entire model. So you have to prepare a little bit when you're doing ABS printing. The one I often use is called PLA. It's probably the easiest to print. It's also the cheapest material that you can get. Con is it has a rather low impact strength compared to the others, so it's really good for prototyping, but not particularly the best if you wanted to use for very high strength applications, unless you really consider the limits of the material and do some structural analysis first. But usually 9 times out of 10, if I'm printing something, I'm using PLA. You also have nylon. Nylon is also similar to ABS in that it has high strength, but it also has the added benefit of being wear and chemical resistant. So that is sort of BME friendly right there. Downside, it absorbs water like a sponge, so it has very low humidity resistance. So much so that if you have any sort of nylon material that you're trying to print with, and you don't put it inside some sort of desiccator, for example, when you try to print with it, you'll hear bubbling and cracking in your printer because there's actually water inside your nylon that is bubbling up and expanding and leaving your filament, and that can cause so many problems in your prints. So you always have to make sure you store nylon in a desk and bag and away from any air or moisture. Next one is PETG. So the nice thing about PETG is it's food safe. So oftentimes if you want to make something like a spoon or any sort of utensil that is going anywhere near food, you could make it out of PETG because it's food grade material. Con, it's rather sticky and stringy to deal with, especially when after it's first been printed. So it's very easy to mess up the print as you're cleaning and handling it. Next one is TPU, and this is by far my most favorite material out of all of them. And it's a very flexible material. It's an elastomer essentially. And by very flexible, I mean I had printed out this small little demonstration heart piece once, and it was about the size of my hand essentially. And then you could essentially just squish it in your fingers and then release, and it will go back to the full shape. So it's very useful for any very flexible designs that you need. Downside is it's very difficult to get accurate printing out of this because remember, you're already dealing with FDM printing, which has the lowest dimensional accuracy. But because you're dealing now with a very flexible material that often has a bit more give to it than any of the other materials, you're not going to be getting a lot of dimensional accuracy from this. So in my experience, I've had anywhere from maybe plus or minus 2 to 3 millimeters off whenever I'm dealing with TPU, which doesn't sound like a lot, but when you're dealing with very specific engineering applications, it matters. And the last one, which is one I've never really used, but I heard it's used a lot in industry, is PEI, which is fire and chemical resistant as a major pro. Downside is it is very costly, by far the most costly out of all the materials. So if you ever want to make anything out of PEI, you have to be very sure about the application for it. And any questions on these filament types?
Yes, we have one question. Which of the filaments is the most accurate generally?
Um, hmm,
I think
definitely not.
I think it relates to the application as well.
Uh, Most accurate. Well, for application, it's whichever one works the best. So if you want something that has a give to it, use TPU. If you want something that is very structurally rigid, use ABS. But if you want me accurate in terms of dimensions, probably best to just stick with PLA because if you stick with nylon, you have the humidity factor. If you stick with ABS, the warping. If you stick with PETG, the stickiness. TPU because it's flexible. This has an issue, and this just has a cost issue. So PLA probably the best, just middle of the road, best option. Anything else? All right. So without further ado, let us continue then. So how do we actually get into doing the 3D printing? Well, first you have to do 3D modeling. So you can go to any of your 3D CAD design tools. So for example, there's this open source Tinkercad, you have AutoCAD, which architectural students like to use. You have Autodesk Fusion 360, which has a free student version that you can download if you want. And if you're an FIU student, you also have access to SolidWorks. So any of these tools are essentially just ways to create a 3D model that you're trying to print. So no matter which of these you pick, make your structure in it, and then you can go ahead and print it. But how do you do the printing? And that's the next step. So generally, when you're doing 3D printing, you want to save it as an STL file. So an STL file literally just has information on all the different triangles and vertices that make up your object. And at least in SolidWorks, when you do an exporting as an STL, you have the option to control the resolution. So you can do a coarse, fine, or change the deviation or angle that is trying to approximate your entire model with. And this has very large implications on how your final print turns out, as it so happens. So here's an example. On the left here, you have a very coarse STL file, so you can very clearly see the little squares making up the model. And it's trying to approximate this jar structure right here. And it captures it, but it approximates it a bit. And over here is a very high resolution. So you can barely even make out that it's made out of a bunch of little squares. So why don't you always just go with the high? Because file size. And generally the larger your file is, the more difficult it is to print or at least to create the print for your printer. If it's a simpler file, then your 3D printer can often process it much more easily. And if you want to see what the actual outcomes are, if you had printed out the left cursor one, you can actually see in your actual print the lines show up, and you sort of lose definition on very fine features like this eagle. And in the very fine resolution print, you retain these features. So it's sort of a personal judgment how much of these are important to you or not. But just wanted to point this out to you. Any questions before I continue? No? All right. So once you have your actual 3D file and you convert it into your STL format, how do you actually give it to your printer to print? So you have what's called the slicing software. So generally there are multiple different softwares that you could use. So we have, for example, Cura by Ultimaker. You have this one called Idea Maker. You have one called Slicer. There's one called Flash Print. There's this expensive one called Simplify 3D. And the literal only point of these slicing softwares is it takes in your STL file or your 3D file, and then it converts it to what's called G code. And G code is literally just 3D printing language speak for how the printer head should move around the surface and how quickly it should feed in your filament to create whatever structure you're designing. So some of these are free, some of these are paid. So for example, Simplify 3D is paid, but it has a lot of nice features. And then you have Cura, which I believe is free, Slicer, which is free. Idea Maker, I believe, has a trial, but it's also sort of free. And then this is FlashPrint, which is the one I use because I have a FlashWorks Finder 3D printer, which is also free. So depending on which one you want to use, they all have the same end goal. So there really isn't a best one. It's whichever one does the work that you needed to do at the time. But in my experience, I prefer using FlashPrint because it's most compatible with my printer. But I've also dabbled with Slicer and Cura, and they have some nice experimental features that are interesting for specific applications in 3D printing. But generally, I'll just throw it into a FlashPrint, and it just works for me. So before I continue, any questions?
I believe some of the softwares actually tell you the pathway as well, the visualization of the pathway.
Oh yeah, they do. So Simplify 3D actually has a nice feature where as your print is happening, it'll show you, as you can see here, how your tool is going over your model in real time. But that's what you get for paying what, like, I think it's like 120 something for this software. But yeah. So now let's go on to some 3D printing tips. So when you're doing FDM printing, remember you have your 3D printing head, and this goes down to like 0.4 millimeter diameter nozzles or something. And it's printing out layer by layer your filament extrusions. So when you're doing this, you have to remember that when you're doing your print, the way you're doing your print and how it's structured matters in terms of its final structural integrity. And what I mean is, if you have, let's say, this structure right here, and you were trying to print it so that when you apply some loads, you apply, for example, this tensile load here, where you pull it on both sides. If you had printed it out vertically like this, it would print it out this layer, then this layer, this layer, this layer, this layer, and going all the way to the top. And then if you had printed out flat like this, it would have first printed out this entire bottom layer, then go up a little bit, and then the entire layer, and all the way to the top. So you can imagine that if it's doing one layer here, then one layer on top, if you pull it on both sides, the only thing that's joining one layer to the one below it is just the adhesion caused by the temperature difference between these two as it fused together during the initial set. However, if you had this entire bottom layer, because of the increased surface area, if you have printed it out this way, you have way more surface area to sort of bind the material with. And what ends up happening is that if you have the loads occurring vertically like this, you get very easy snappage occurring right along the layer lines. However, if you had printed it flat, it's much more difficult to break the material. So how can you know beforehand how the way you should print? Well, one way you can do it is do some FEA analysis. So for example, if you quickly throw this into ANSYS, SolidWorks, and I believe there are some online FEA tools that you can use, you can apply some simple loads to your geometry. And I believe Autodesk Fusion 360 also has these tools. So you can apply loads here, fixtures on both ends as well. And you can see you have a stress concentration building up here, and the stress sort of occurs vertically. So you can also take a look at the orientation of it, and you can see here that the orientation for the von Mises stresses are occurring vertically. And if you notice here, the edges are where it's concentrated at, and that's exactly where it broke off over here. But the internals, you can see by this sort of parabolic shape, the internals seem more structurally rigid, which is what you got here. So there's less stress occurring inside than outside. So you can use this information to sort of change your model a little bit, make it more structurally rigid, or you can go ahead and print horizontally instead of vertically to sort of bypass these effects. Any questions before I continue?
I think for those that I'm not sure what FEA is, it stands for finite element analysis.
Yes.
Or finite element modeling.
Yeah, so finite element analysis, you essentially take your 3D model, you mathematically solve a series of different equations across the entire structure. And essentially, you can remember when you're doing force by diagrams and figuring out the forces on its own little body back in physics. It essentially does that, but across the entire structure. So based off certain forces and what's moving, what's not moving, you can figure out the stresses throughout your entire structure, which is very useful when you're making something. Next thing I want to highlight is supports. So because you're inherently printing something layer by layer by layer, you always need to have something to print on. You cannot print on thin air. So you have what are called supports, where if you have, for example, this Y shape that you're trying to print, anything that is sort of floating in midair like this is called an overhang. Now, how much of an overhang you're allowed to have varies, but generally a good rule is 45 degrees. So you have any sort of feature in your model that is more than 45 degrees, I would consider removing it. But if it's less than 45 degrees, generally you can get away with just leaving that there because you can do a struct print here. Then the next layer sort of has enough of the layer below it to support itself, and then you can get away with doing the overhang. But if you have too much of an overhang like this, say this 60 degrees, then it can't print on midair, so you're gonna have to have a support here. And that's what ends up happening if you have this bridge. You have literally nothing to print on, so you need to put supports, and you have literally nothing to print on. This is a full 90-degree overhang, so you need supports here. However, there is a caveat to this rule. Because printing is inherently going fairly quickly over a short distance as the printer head moves, you can generally get away with printing over thin air if it's a very small gap. And generally, you can get away with printing over 5 millimeters. So if anywhere in your model you have a gap of at least 5 millimeters, you don't necessarily need to put supports there. You can just sort of leave it hanging. But you can see as you get wider and wider and wider, because you're inherently sort of printing on thin air, your filament sort of droops. So it gets worse the more off you get. So I keep saying if you have these supports, sometimes are required if you have overhangs or not, but why don't we just put supports everywhere? Well, downside of that is you're using up filaments, you're using up material, and that adds waste and cost that you have to remove. And any type of supports you put into your model, that actually adds to your time. So look at this little teapot that we're trying to print here. If we print it without supports, it's 3.5 hours. If we print it with supports, it's 5 hours, a full almost 2-hour difference. And if you look here, you have sort of this curve that's occurring here, which seems to be fairly sub 45 degrees, maybe except for this point right here, but you might be able to get away with it. And you have this nice curve up in here, and except for maybe this inner part here that's floating. So if you intelligently make your supports, you may be able to get away with only having to put supports inside here and maybe only at the tip here. And you can get away with not having to put supports everywhere. And naturally, because the supports are inherently part of your structure, you have to remove them afterwards with clippers and such. So it's always just a pain. So one way that you can get around doing this is over here, where you make your model. So in this case, it's a little sculpture that has features in it that are their own supports. So you can imagine here, there's this rod structure right here that is sort of affixed to the bottom of this base, and the hand is grabbing it. So there's no part of this structure entirely that is beyond 45 degrees. So this can print entirely on its own perfectly. But if this arm was just floating here without this rod, then it would need supports. Or if this rod was just here by itself, then perhaps it wouldn't have the structural integrity to stand on its own and it would need supports. And one more thing for CAD modeling purposes, you usually have the option to put sort of rounds on your edges. So we usually call them fillets or chamfers. Avoid fillets as much as possible because this continuous curvature here does not make for easy or nice type of layering, because it gets steeper and steeper and steeper as you go. So the first layer is this, then the second layer goes all the way over here, then the third goes even further, and then it usually only stabilizes after you go above. So replace all fillets with chamfers. You'll just have better support structures in the long run. And the last thing you can do is physically change how you're printing your model. So if this is your model and it's sort of some stickman thing, and this arm is just floating in midair right here, you're going to need to put supports here. But what if you just tilt your model in such a way that it's sort of facing off a little bit so that no part of it is actually beyond 45 degrees with respect to how it's printing? And now you can get away with printing only supports down here. And in my experience, I would probably put maybe one support here for the head, but that's just me. So you can get away with doing that to avoid supports. Any questions? So next thing is when you're doing your 3D printing, you often have what's called infill. So this is what's going on inside of your model. So you can't have your model just be empty. There has to be something inside of it. So you have your option for infill patterns like Hilbert, Honey, 3D Honey, Grid, whatever. If you want to do a fast print, I suggest you pick what's called a grid pattern, which is literally just a grid going in one direction or the other, or you go with lines. If you want to have internal structural integrity, you can go with the honeycomb model info pattern, which is a honeycomb and is structurally rigid. You can also go for cubic, so that goes in 3 dimensions, or octet. In my experience, I always prefer to use honey or grid. It's just generally what I like to use. You can also use infill density. So 100% corresponds to the entire model is made out of your material, and generally that's overkill. Likewise, if you have 0%, you literally only have the edges of your model, and the inside is completely empty, which does not make for a very structurally rigid part. And in my experience, pretty much 10% is ideal. You don't need to go beyond that. And if you want, you can do 100% for some very small pieces where it doesn't make that much of a difference to go 100 or 5 or 10. But as a default value, I always stick with just 10%. It just works for me. Next thing I want to talk about is the nozzle and bed temperatures. So remember how I was talking about ABS generally has this warping issue? Well, the bed you're trying to print it on has to be heated because of that. So you have to actually heat the surface that you're trying to print on between 80 and 100 degrees when you're doing ABS printing, and your nozzle, so the tip that's actually doing the printing, has to be between 230 to 240. PLA, you don't actually even need a heated bed for PLA. You can just use the nozzle temperature between 210 or 220. And generally for the rest of these, I would use these settings. And the only ones that really require you to have a heated bed is ABS, nylon, or PEI. I've been able to print PETG, TPU, and PLA without having a heated bed, and it works just fine for me. You can see here what happens if you don't take care of your bed temperature. So I believe this was printed using, I can't remember what the material was. Forget it. But you can see here how it's 180, 190, 200. And if you go outside your temperature range, that's ideal. Then you start getting stringiness happening because the material is still molten as it's being printed. That's why we have these specified temperature ranges that usually is written on the filament. So before I continue, any questions? Nice. So next thing, bed leveling. So because you inherently have to print layer by layer, it's very important that your first layer that you're printing is as accurate as possible. Because if you don't, you're going to have a print that isn't sticking to the bed because the first layer didn't adhere. You can have gaps in your layers as it's doing the printing, or because your bed leveling is inaccurate, you get spludges or gatherings of plastic around the head as it's sort of moving around. So this could cause issues if you don't do bed leveling correctly. So just show you this a bit more. If you go too low and your bed isn't, if your head is way too close to the surface, you're sort of putting excess material as it's going and it sort of droops on either end. If it's too high, then your printer head is up here, but the surface is down here. You get very poor bonding. So the best is when it's just right in between and you get nice adhesion between the layers. You can see here if you're too far apart, it's like this. Too close, you get waviness. It's always in between where it's nice and perfect. So if you're using the common 0.4 millimeter nozzle that usually comes with most printers, you want your head of your printer to be about 0.1 to 0.2 millimeters above the surface. So how do you go about doing this? Well, some of the fancy printers nowadays have an auto bed leveling feature. That if yours has that, congrats to you. Just use that, and you pretty much don't have to worry about this. But if you have one of the older style ones, which is usually all of them, you can use an index card which has the perfect 0.1 millimeter, 0.2 millimeter thickness, and you can slide that right beneath your printer head. And you basically adjust what are called bolts or knobs with springs beneath your entire printer bed, and you can adjust them until your paper, which is sort of representing your first layer, just barely scrapes against the tip of your printer. And then once that happens, you'll know you'll have leveled properly. So any questions?
Yes, I believe some printers now they do it algorithmically, so
Yeah.
they adjust those knobs so you don't have to do it manually anymore.
Yeah, some of the nicer ones too. Always jealous of those, but I still go old fashioned and I do it myself. Yeah. All right. So some currently available printers. This is a bit outdated from when I made this, but you have, for example, the Creality Ender 3 Pro, so that's 250. The one I have at my house is the Flashboard Finder, which is sitting right next to me actually. You also have the very popular Prusa series, so this is more expensive, 749, and you can also get one of the more fancier ones, which is 899, the Flashboard Streamer, which has an enclosed surface and dual printer heads. And like I said earlier, you can generally now get this for sub $100 if you look. And I also mentioned that RepMap was the one who created the open source framing for it back in 2005. And you can see here the Creality and the Prusa look very similar, and that's because people use a RepMap design. So as far as us BME students go in FIU, we actually have 3 printers in the BME Creativity Lab. We have the MakerBot Replicator Desktop 3D printer, which costs $2,700. We have the Prusa i3, $749, the Ultimator 2, which is about $3,000. And I believe we recently got another printer, but I don't know which. And if you want to use any of them, you can go ahead and contact Dr. Yun, and you just tell her what you need it for, when you're gonna use it, and she'll let you use it after some training, naturally, if you're not a grad student per se. Any questions?
Yes, we have one question. What type of training would be required in order to be able to use these printers?
So back when I needed it for this very specific purpose, I was already a grad student, so she already trusted that I already knew how to use it. But I imagine she just asked one of her students to quickly teach you how to use the printer, change filament, set up your prints, and some basic thing like that. But I don't know the details of it. You'd have to ask Dr. Yun specifically.
Yes, I could add on to that. I actually went to her once, and she gives you a handout from MakerBot directly of the steps that you need to know to be able to operate it. And once you read those steps, then she'll guide you through it. It's probably different now, but there are other options available on FIU, like the Honors Edge Lab. I think we're good.
All right, so continue. So here are some personal examples, just in case you wanted to see it sort of used in real life, I guess you could say BME applications. Here's a mitral valve holder I made in SolidWorks, and I'm printing using TPU, that flexible material. And we essentially had teamed up with this company called Core Matrix, Cardiovascular Regenerative Institute, whatever. And they had created these biomaterial um, uh, valve holders, valve material, and I had made these micro valve holders to suture this material too, and we put it inside of our pulse duplicator in our lab to mimic how the valve is going to open and close. And in this case, it's the micro valve with 2 posts, and then we also printed one with 3 posts for the aortic. And you can see here in our actual pulse duplicator, the structure opens and closes, and it works perfectly. Now we could have taken the steps and made a nice structurally sound print from some third-party company, and then it probably would have cost us an arm and a leg and to get shipped and everything. I quickly printed this within the span of 20 minutes, and we were up and ready and testing it shortly after. So one of the applications here. Next thing is a bioreactor that we printed for conditioning our cells. So we have cells essentially that are on this sort of torpedo shape here, and they sort of grow inside this structure here that we print, and they're exposed to this fluid environment that we determine to be optimally stable for cell growth. So all parts of these are printed or machined. So that essentially saves us a lot of the cost. And you can see here is the flash forward finder that we have in our lab. So we can print with 2 different materials at once. And that's how we made the majority of the structures here. And then this is just a fancy little CAD model showing all the different pieces. So with that, I just want to leave you guys some resources that you can use. So Thingiverse is a nice site if you want to have access to some free materials to do 3D printing. CG Trader is also a nice one, Sketchfab as well. And any questions?
Right. Well, I just want to thank you, Asad, for the presentation. Thank you guys for coming. Right, we do have one question.
Yeah.
What programs do you use in 3D printing?
So I already mentioned this briefly, but for the actual creating of my structures, I generally make it in SolidWorks, and then when I want to do my prints, I use the Flash print. So I think I can actually do Flash prints. Do you see the software on my computer?
Yes, I think we can see it.
All right, so this is the Flash print software that I use. It's the one that came with my printers. It's the nicest one in my experience. So you can just quickly load up some file. Let's say I'm printing this snake thing. Here's the demo file. You can import your STL. You can move it around. You can scale it, whatever. And then you have the option of putting supports. So if you have any problem areas that are just floating around, it automatically creates supports for you, but I don't even think supports would have been required here, but it has the capability. And then you can actually go ahead and do your 3D printing. So as I mentioned, you have the option of controlling your infill density, the pattern that you use, the perimeter count, so how many outside structures you require. You can go very deep into it, and how complicated you want all your settings to be, which goes way beyond the purpose of this workshop. But whenever you're happy with whatever you have, you can say okay, print it, and then it does the slicing as I mentioned, layer by layer. So you can imagine here, this is the very first layer that gets printed, and you can see here an estimation of this print would take 55 minutes. It's going to use this much material, and it does it layer by layer. And you can see the infill density right here, and it creates it layer by layer by layer. And even though it looks blocky here, we're looking at it at a sub-micron scale, but when it's actually done printing, it's usually fairly smooth, and you have to really look closely to see the layer lines. And if you want to get rid of the layer lines, you could always just print at a higher quality, or just go at it with some sandpaper, either or. I believe you had a question?
Yes, we have one more question. Is SolidWorks good for modeling when planning to bioprint something?
For a bioprint, I'm not entirely sure. If it's any general structure, if you can make it in SolidWorks, sure, go ahead. Because a 3D object is just a 3D object. You can make it in SolidWorks, AutoCAD, Blender, whatever. The point is to get the STL file. If whatever you're using can produce an STL file, you can 3D print it.
Yeah, in those projects that you showed us, did you use what materials were you using?
So let's start off with this one. So this holder was made out of TPU. So this was supposed to be a valve holder that we put this scaffold material that we got from Core Matrix. So inherently, I needed something that was a bit flexible, so that's why I used TPU, and that's pretty much it. So it had to fit snugly here, but also sort of have a little bit of give to it because of the fact that it's going to be exposed to fluid, so it could jostle in place a little. So that's why I printed out this flexible material. And then over here, I printed this out of PLA and then we had to sterilize it naturally. And then the outside of this was made from a single block of acrylic. So this was machined elsewhere. But this black internal here, this connection piece here, that's all 3D printed. Any other questions?
So based on those different materials, do you tolerance how you print them differently?
Oh yeah, I have entire spreadsheets and protocols dedicated to making sure my tolerances are perfect. So for example, the torpedo here and the surface here, I know that they are exactly 3 millimeters apart from each other when you put these holder rings in. And it's vital for my application that it's exactly 3 millimeters because I run fluid simulations, and having a gap of that 3 millimeters or whatever is the perfect gap I need to induce the fluid conditions and the shear stresses and the velocity contours I require that are most favorable for cell growth. So I take the tolerances as far as 0.1 millimeter differences really strictly. That's why I was emphasizing them throughout the presentation.
Yeah, I have one. Where do you think the future of 3D printing is going? Just your personal opinion.
Personally, probably going to be more easy to use, more in-home, do-yourself. So with the cost running down, I can easily see most people getting access to a very small printer, maybe when they're very young, just to do some small little fun 3D prints. And then companies now, rather than for example, building a part and then sending it to you, when you buy something, maybe they'll just send you the file for it. And it'll be some sort of proprietary file that you can print, let's say this small little extra device thing that you need for some machine. So rather than the company having to make the product, send it to you or whatever, maybe they'll just, when you buy your material or you buy your product, they'll give you 3D files to replace parts that you might need under some sort of agreement or something.
Thank you.
So if there's nothing else, I'll stop sharing my screen. All right.
Thanks again, everyone, for coming. We'll be holding hopefully more workshops like these soon. And just for the record, we plan to release this onto our channel so all of you can see as soon as possible. But thank you for being part of the experience, guys. Hope you enjoyed it. And thank you, Asad, for being the speaker in this.
No problem.
Thank you, Claudia, as well, for collaborating.
Bye, Alejandro.
Bye, guys. Thank you.
Take care, guys.